Hey guys, Jake here, coming at you with another math problem today. Today I'm going to be showing you an example of using implicit differentiation with trig to find the equation of a tangent line at a given point. And I wanted to do something a little special today, so when this video gets 10 likes, I'll be coming out with a bonus video for you guys. So be sure to hit that like button down below and drop a comment to let me know what you want that bonus video to be about. And let's go ahead and just jump right into this problem. So here's the problem we're going to be doing. We're going to use implicit differentiation to find an equation of the tangent line to the curve at the given point. The curve we have is sine of x plus y equals 2x minus 2y, and the point that we are given is pi. So this is a great example of what it looks like to do implicit differentiation with trig. And what you want to keep in mind when you're doing these tangent line equation problems is the equation of a line is always going to follow the same general format. We're going to be looking for something that looks like this. Y equals m times x minus x0 plus y0. So that's just the general form of a line, right? Where you have a slope of m, and then it goes through the point x0, y0. So x and y are going to remain as x and y, but what we need to do is kind of fill in these three blanks of m, x0, and y0. Well, like I said, x0 and y0 is just the x and y coordinate of a point that we know this line lies on. Well, in order for this line to be tangent to this curve at this given point, we know that it has to go through this point. So right off the bat, we already know that x0 is going to be pi because we have an x coordinate of pi. And we also know that y0 is also going to be pi because we have a y coordinate of pi. So all we really need to do is figure out our slope, our m, in order to find this tangent line equation. Well, to find the slope, you should automatically, your brain, whenever you hear slope, should go to derivative. Implicit differentiation is a form of finding a derivative. So we're going to use implicit differentiation here to find the slope of this curve at this given point. So to do that, what we're going to have to do is essentially find dy dx. So that's basically what this problem is to find dy dx. So since we're trying to find dy dx, like I've done in some of my other implicit differentiation videos, what we want to do is kind of think about which letter of this x or y, which letter is a variable and which letter is a function. Well, since we have the y on top and the x on bottom, and this is generally going to be the case when you have x's and y's, usually your x is going to be your variable, your input variable, and y is going to be your output, which is going to be a function of whatever your variable is. So in this case, y is a function of x. So in order to find the slope of this curve, we just need to take the derivative with respect to x of both sides of this equation, and then we're going to solve for dy dx. So to do that, we're really just taking the derivative with respect to x of each piece. We have kind of the sine of x plus y as one piece, we have 2x, and then we have minus 2y as another piece. So we'll just kind of take them one at a time. First of all, to take the derivative of sine of x plus y, this is going to require the chain rule, because the chain rule is used whenever you have one function basically being plugged into another function. So in this case, we have x plus y, or in other words, the stuff that's inside the parentheses here is like our inner function, and then the sine is our outer function. So chain rule says we would take the derivative of the outer function. So the derivative of sine is going to be cosine, and we leave our inner function alone. So we leave x plus y as x plus y. We don't want to change our inner function yet. But then what we want to do is multiply that by the derivative of our inside function. So then we're going to multiply that by the derivative of x plus y. Well, the derivative of x plus y with respect to x is going to be basically just the derivative of x with respect to x plus the derivative of y with respect to x. So since x is our variable, since x is the thing that we are taking the derivative with respect to, the derivative of x with respect to x is just going to be 1. The derivative of just your variable is going to behave the way you would expect it to. However, now when we take the derivative of y with respect to x, you want to keep in mind that y is a function. Y is a function of x. Of course, we don't know what y is. It hasn't been given. There's not really a way to figure it out. But we know that y is some unknown function of x. So when we take the derivative of y, we can't just say that it's 1. because that's the derivative of x with respect to x. The derivative of y with respect to x is dy dx. So this dy dx notation, it basically, you can kind of just think of it as saying the derivative of y with respect to x, which when you don't know what your function y is, that's really the best you can do to find the derivative of y, is just kind of use this notation that literally just means the derivative of y. So then we can close our parentheses here, and then we can move on to taking the derivative of each of these terms on the right side of our equation. So the derivative of 2x, again, since we're taking the derivative with respect to x, the derivative of 2x is going to behave basically the way we would expect that derivative to behave. It's just going to be 2. And then similarly to finding the derivative of the y that we had to do over here, the derivative of minus 2y is just going to be minus 2 times the derivative of y, which again is just dy dx. So now that we've taken the derivative of both sides of our equation with respect to x, what we can do is kind of expand everything out, and then we're going to want to get all of our dy dx terms on one side of the equation and all of our non-dx or dy dx terms to the other side of the equation. So first of all, we'll just kind of distribute out these parentheses. So cosine of x times y times 1, or x plus y times 1, it's just going to give us cosine of x plus y. And then cosine of x plus y times dy dx is just going to give us dy dx times cosine of x plus y. And then on the right side of our equation, there's not really anything we can do to simplify or expand this out, so we can just leave it alone. And then, like I said, what we want to do is either add or subtract all of our dy dx terms to one side of the equation and move all the others to the other side. So we'll go ahead and move all of our dy dx terms to the left. So we'll add plus 2 dy dx to both sides of our equation. And then we can go ahead and subtract over our non-dy dx term from both sides of the equation. And that's going to cancel this piece here, and it's going to cancel this piece here. So we're just going to get dy dx times cosine of x plus y plus 2 dy dx over on the left side. And then on the right side, we're just going to have 2 minus cosine of x plus y. So the reason why we wanted to do this is now that all of our dy dx terms are on the same side of the equation, what we can do is actually factor out dy dx from the entire side of the equation. So if we pull a dy dx out of this term, that's just going to leave us with cosine of x plus y. And then if we pull dy dx out of this term, that's just going to leave us with a plus 2. And the reason why that's so nice is now what we can do is just, in order to get dy dx by itself, we just have to divide this whole thing in the parentheses that's being multiplied by dy dx to move it over to the other side of the equation. So doing that is just going to give us dy dx equals everything on the right side over here divided by everything within the parentheses here. So now that we've solved for dy dx, remember the reason why we did this. Dy dx represents the slope of this curve at whatever xy point you plug in. So since we know that we're trying to figure out what the slope of this curve is at this given point pi pi, what we want to do is plug in pi for x and pi for y in order to get the slope of this tangent line equation that we're trying to find. So if we plug in pi for both x and y, basically that's just going to make what's in each of these parentheses here be 2 pi, because we're just going to get pi plus pi. So cosine of 2 pi is just 1. So each of these cosines are just going to become 1. So plugging in pi and pi is going to give us 2 minus 1 over 1 plus 2, which is just going to be 1 over 3. So we know that the slope of our tangent line has to be 1/3. And then all we have to do, like I said, is plug in pi for both x0 and y0 as well. So doing that is going to give us our tangent line equation of y equals 1/3, because that was the slope that we found. Dy dx equaled 1/3 once we plugged in pi and pi. And then x minus pi plus pi. And then we could simplify this a bit further by distributing the 1/3, and that's going to give us 1/3 x minus 1/3 pi plus pi, which is just going to give us y equals 1/3 x minus 1/3 pi plus pi is just going to simplify down to 2/3 pi. Hopefully you found this video helpful. If you did, please be sure to hit that like button down below, hit the subscribe button as well, and that bell icon so you're notified of all my videos. And like I said, as soon as this video gets 10 likes, I'll go ahead and come out with a bonus video, so be sure to hit that like button. And if you want to check out any other videos about implicit differentiation or finding the equation of a tangent line, go ahead and click on one of those videos over there. Thanks, and see you next time.